So our next topic is going to be C++ bidirectional iterators. And a bidirectional iterator is designed to allow algorithms to go both forward and backwards through a container. And so you can imagine that the bidirectional iterator has all the same characteristics that a forward iterator does, which of course in turn has all the characteristics of an input and output iterator. And then they also add the ability to do pre and post decrement of the iterator. So you can basically do the minus operation. Many STL containers implement bidirectional iterators, including the various associative containers we're going to be talking about, the various sets and maps and unordered sets and unordered maps and so on. And also the list sequential container implements a bidirectional iterator. Recall that the forward list only implements a forward iterator, not a bidirectional iterator, because it doesn't have a previous pointer in its node, so it can only go forwards but not backwards. So I'm in my 4.6a example, and this is going to discuss a bit about bidirectional iterators, and then we'll show some code that illustrates how they work in practice. So basically, as we've kind of alluded to before, you have all the operations that are supported by forward iterators, including constructors and assignment operators, equality and inequality operators, the dereference operator on both sides of the assignment statement, in other words, both an L value and an R value. And then it also supports pre and post increment and decrement. So all the same operators that we've come to know and love with C++ and C pointers with respect to incrementing and decrementing. So here's a very simple example. We're going to create ourselves a list of ints, and the list will initially have the size of 1, and the list will initially have a value of 1 in its one element. So that's what the constructor does for a list. And then we go ahead and we add an element at the beginning of the list and at the end of the list. So pushback will add the element at the end of the list, so it'll be 1, 2, and then push front will add an element at the beginning of the list, so it'll be 0, 1, 2. And now what we're going to do is we're going to go ahead and get ourselves an explicit iterator to the beginning of the list. And I do this just to compare and contrast between saying list : iterator, which is the explicit way of doing things, versus using the auto way of doing things. So just for kicks, I use list : iterator to get the first element, and then I use auto to get the last element. And then once I've got first and last, as you can see here, while last minus minus is going to be greater than or going to be not equal to first, then I'm going to go ahead and print out the contents of the last iterator. So obviously what this is doing is it's printing things in reverse order. So let's go ahead and take a look at that. And when it compiles, then what we should get here is an output that says 2, 1, 0, which of course is the reverse order of the list. A couple things to note just to make sure you're comfortable with this. Notice how we have the post decrement operation here. So it reads the value of last, compares it against first, and then it does the decrement after it reads the value of last. So the current value of last is what's compared against first, and then last is decremented. So by the time we determine that we haven't reached the end of the list, the end of the iterator range, then last is going to point to the previous element. And so we're always going to be printing out something that's a valid iterator. And we have to do that, of course, because remember, the last iterator always points 1 past the end. So hopefully I'm not beating a dead horse, not that we want to beat dead horses, of course, but hopefully I'm not overemphasizing this, but it's a very easy mistake to make, to forget that you can't actually ever access the iterator returned from last. You always have to decrement it by 1 before you increment it. And you'll also notice that we only do the minus minus operation here. We don't try to do anything more interesting with respect to pointer arithmetic. And in fact, it wouldn't work if we tried it, because the iterators are only bidirectional iterators. Okay, so that's one example. Now let's go ahead and take a look at another example of the so-called bidirectional iterators. And this is going to illustrate how to use a bidirectional iterator with the copy and reverse copy algorithms. And it'll also give us a chance to talk about the difference between in place back and pushback on containers. Now, in this particular case, we're using a list, but the concept of in-place back and pushback are also relevant for other containers as well, other sequential containers, such as vector, such as deck, and so on. So we're going to illustrate this as usual, we're going to use our simple string class because we've instrumented it so you can kind of see what's going on under the hood. So what we're going to do here is we're going to make a list of simple strings called a list, and then we're going to go ahead and do in-place back. And you'll notice how we're passing in a string, a character string literal. So what that means is that this particular implementation of simple string is not designed with an explicit constructor. So this will do what's called implicit conversions. And I did that on purpose here to illustrate the point. So we can do in-place back peach, apple, bananas, and then we're going to go ahead and push back peach, apple, bananas again, except this time we're going to use the pushback operation instead of using the in-place back operation. And you'll see when we run the code that this has higher overhead. And so this makes a difference. The choice of in-place back versus pushback makes a difference when we have more complex classes that we're going to be inserting into our containers. If this was just int, for example, it wouldn't really matter. But when we start getting things with more complex semantics to make constructor and destructor calls and so on, then in-place back and pushback really start to differentiate. And in fact, you can see that that's the case because the compiler is trying to tell us, hey, hey dude, don't use pushback, use in-place back. So it's trying to get us to make these changes. And I'm choosing not to listen to the compiler at this point because I want to show you the difference. But it'll try to warn you if you make the wrong choice. Then what we're going to do after we've gotten the elements pushed onto the list, we're going to go ahead and create a second list we call B list, which has got as many elements as there are in A list, but it starts out initially empty. It just has that many elements in it. And then we're going to go ahead and do a reverse copy. So we're going to copy from the end of A list to the beginning of A list, and we're going to copy all the contents into B list. And then we're going to go ahead and print the results. And then just for kicks, after we do that, after we use reverse copy to put things into B list, then we're going to go ahead and print the results backwards by using rbegin and rend. So we'll take a look at that. rbegin and rend, of course, are going to be iterator adapters that take forward iterators and turn them into reverse iterators. And that's exactly what reverse copy doesn't do that, but you'll see how reverse copy works as well. We'll take a look at the code in a second. Okay, so let's go ahead and take a pass through this code, compile it, and then we'll see the output. So let's first just take a look at the output. You can see there's a lot of output here, and that's because I'm using the simple string, and recall that simple string has lots of instrumentation calls, so you can see what's specifically going on under the hood. So the first thing I want you to observe here is the fact that the work required to do the in-place back, which is this stuff up here, in-place back is way, way shorter than pushback. And that's because in-place back has this magic, you can see here, that will go ahead and basically insert the element at the end of the list, and it forwards the arguments using the STL forward method. And it also, if you take a close look here, you can see that this method is defined as a member function template as opposed to a template member function. And a member function template in this case is taking a variadic list of template parameters. And so what's going to happen is that variadic list of template parameters is simply going to be forwarded to insert. And so as a result, there's only one call to construct the simple string, and that one call takes the character string that's passed in here. If you take a look over here, it takes the character string and it just goes ahead and in-places it, and that ends up calling the constructor that takes a const char star and makes a simple string. So that's really, really efficient. In contrast, if you take a look at pushback, you can see that pushback has to call that operation, that constructor in simple string that converts a const char star into a simple string. And then if you go take a look at what pushback does here, it's going to end up calling the insert operation with the move semantics. So that's what triggers this particular call. So we're going to end up doing the move semantic version constructor, the move constructor, to take the contents of this simple string and then move it into the where it needs to go. But that will then also trigger the need to call the destructor. And even though the destructor doesn't do very much, it's still getting called. So as you can see, there's about 3 times the amount of work required for, or 3 times the amount of calls, not really the amount of work, but 3 times the amount of calls for this particular implementation. And that's again why we should prefer to use in place back over pushback. Even though pushback does have some optimizations built into it, it's still better to go with in place back. And in fact, we'd get even more overhead if we actually made an instance of a simple string and then did a pushback on that. That would cause yet even more overhead, because we'd call the version of pushback that does a copy constructor. So that would be even more overhead. Okay, so once we're done with all that stuff, then you can see that we actually go into this code down here, and we're doing all the reverse copy stuff and so on. And you can see that when we do the reverse copy, we end up with saying bananas, apple, peach, bananas, apple, peach, which is in reverse. And we stick that into B list. And then down here, we go ahead and copy the results into B list. And then we do a reverse begin, an R begin and an R end, and that ends up taking it and printing it back out in the original order, because we took the reversed copy and then reversed it. We printed it in reverse order. So these are just illustrating a few of the things you can do with STL. And of course, what's really going on under the hood is that we've got these iterators that are doing their thing, going either direction. So let's take a quick look at some of the code here just for completeness. So here's reverse copy. And you can see that what reverse copy does is it takes a bidirectional iterator and an output iterator. That's what the template's provided. And then reverse copy itself takes a first and a last, which are bidirectional iterators, which work fine with lists, because that's what the type of iterator is for a list. And then it takes an output iterator. And as you can see, what it does is it walks through the range from beginning to end, but every step along the way, it first pre-decrements last, so it'll be a valid element to dereference, and then it copies from the last iterator into the output iterator, and then increments the result by 1. So basically what it's doing is it's just walking backwards through the list after first decrementing the bidirectional iterator last, and then it keeps doing that until it reaches the beginning of the list. So that's what reverse copy is doing. So it's just a reverse of the normal copy. Then down here, if you take a look at R begin and R end, you'll see that what they do is they actually end up returning reverse iterators. Now, I'm not going to spend a lot of time talking about reverse iterators at the moment, because we've got a whole section coming up later on reverse iterators. But in a nutshell, what a reverse iterator does is it's an adapter that takes a forward iterator and turns it into a reverse iterator. So what it does basically in a nutshell is that the plus plus operation on a reverse iterator actually does minus minus. So it's kind of like Bizarro world, where everything's turned around and goes backwards. Okay, so that is another interesting example. So not only did we get a chance to talk a bit about bidirectional iterators, but we also got a chance to talk about optimizations like in place back. And I think in one of your upcoming assignments, perhaps assignment number 4, will actually give you a chance to implement the in place style operations on your array. And that'll be fun, because it'll give you a chance to learn about this optimization in STL and C++.